In this segment, we're going to be talking about circle geometry, and I'm going to be touching on inscribed angles, central angles and their relationships, chords, and tangents. So here I have my circle with a center at point B and an angle that I've produced that starts on the edge of my circle to the center of my circle to the edge of my circle. This is called a central angle, as we talked about in the last video, and it's got a measure of 77.38. Now, what a lot of students don't understand is if I make my circle bigger, what's going to happen to my angle? And they can see as the circle gets bigger, the angle doesn't change. The length of the radius changes, but the angle itself does not change. And so the central angle doesn't grow if my circle grows. When I produce this angle, I produce an arc. We called it the minor arc, which is the one inside here, and the major arc, which goes around the outside. And so this minor arc, we can say it's inscribed by A and C. So angle ABC is inscribed, or inscribes this minor arc. Inscribed is just a fancy word for saying ends at the end, or subtends. So the word subtend just talks about where the arms of the angle end, and we can have a minor arc subtended at A and B. Now if I modify my picture a little bit and I cut it into 4 equal segments, we can talk about this angle. We see that it measures A to B to C measures 71. If I cut my circle into quarters, what would the angle have to be if I took my angle and measured it up to that? So if I try to get it pretty much on that line and onto this line, I can see that I'm going to get a 90-degree angle. And we can get students to predict the angle based on how many segments my whole circle is in. My whole circle is made up of 360 degrees. I now have 4 segments, so 360 divided by 4 gives me a 90-degree. If I was to continue to cut these up, we can ask the students to predict what that central angle would be. So we've talked about 360 degrees. If it was cut into 4 sections, each section would be 90. If I cut each section again into half, I would have 1, 2, 3, 4, 5, 6, 7, 8. So 360 divided by 8, what would that measure have to be? And I could go up and kind of measure one of those angles. We could do it to say here and here. And I can see, well, it's going to be pretty close to 45 if I'm doing it by sight. And I could actually predict what it's going to be if I do the calculation. 360 divided by 8 equal segments, equal being key, each one would have to be 45 degrees. And we can have the students work on trying to estimate or calculate what the angle of the central angle would be. Central angle coming from the center of the circle, inscribed at the ends of my circle. So now I'm going to talk a little bit about inscribed angles. Inscribed angles, instead of starting at the center of the circle, they start at the edge of the circle. So the vertex is on the edge of the circle. So A to D to C would be called an inscribed angle, as opposed to A to B to C, which is the central angle. Now, both of them are subtended at points A and C, and so they both produce the same minor arc. Now, if I have an inscribed angle that goes to the same points as my central angle does, there's a relationship that we need to know. And if I move this around, it doesn't really matter where this inscribed angle is going to be. It always ends at the same points A and C, which is the same endpoints of my central angle. And so if my central angle is inscribed to the same points as my inscribed angle, subtended at the same points, then we can see there's a certain relationship. If I take this orange angle, I know that it's going to be half the size of the central angle. And if I change my central angle, so it's a bigger angle, 63 ABC, my orange angle is going to be half of that, 61.58. And it doesn't really matter where I put it. You'll notice that it doesn't really change. As soon as I change what my central angle is, my inscribed angle always changes. It's always half of what that central angle is. So my inscribed angles are half of my central angle. So inscribed angles are 1/2 of the central angle, but that's only if they are subtended at the same points. Okay. Now, the other thing about inscribed angles is if I made another inscribed angle, we could notice that it's also 1/2 of the central angle because it's inscribed to the same points. It inscribes the same minor arc. It's subtended at the same points A and C, and so it's going to be half of that central angle. Well, if this is half, the orange one's half, and the green one's half of the same angle, these two angles would be the same measure. And notice that an inscribed angle here is going to be the same as the inscribed angle here, 16.7 degrees. So if I take the central angle away from that picture and just show two inscribed angles going to the same minor arc, subtended by the same points, then we're going to notice that the two inscribed angles are of the same measurement. So if they're inscribed to the same points, then we should be able to make the same measurement. So if I take that idea that my inscribed angle going to the same endpoints is half of my central angle, what would happen if my central angle was going all the way across if it was the diameter? So I've had the computer create a diameter, and we can see it goes through the center of the circle. And if I make an inscribed angle like this, and I've got my blue inscribed angle going to the same points as my central angle goes, then there's going to be something that happens with this angle. We know this angle is going to be half of this inscribed angle, but this is a special central angle, and it's got a measurement of a straight line. Straight lines we know are 180 degrees, so this one would have to be half of 180 degrees, so it's going to be 90 degrees. So I've asked the computer to measure that for me. So a straight line is going to be 180 degrees, and it doesn't really matter where I put my straight line. It's always going to be 180 degrees. My angle FHG subtended at the same points, so it inscribes the same arc here, is going to be half of it, so it's going to be 90. And if I move this across, notice that it's always going to be 90. And that makes sense because it always is ending up at the same 2 points. And so we get this special situation of this inscribed angle when it is inscribed to the same points of a diameter, because it's always 180 for my diameter, so therefore it's going to make a right angle of 90 degrees. So in this diagram, we're going to play around with those concepts again in a slightly different way. So if I give you that angle IJK is 70 degrees, so this angle inside here in the blue one is equal to 70, and I want to find out what is this one inside the red one, ILK, we can use our central and inscribed angles to figure this out. So I'm going to create an angle here between I, B, and K. I'm going to create a central angle. And there it is in green, and it's going to the same points, so it's a central angle, so it has to be twice this angle. So I know this one's going to be about 140 degrees. I'll have the computer measure it, and it comes out to 140.14 because of the decimals, and I can't get rid of those decimals right now, so we're going to use those decimals. And we're going to use that idea now. If this angle up here is 140, what's the angle from I around here? So what is this big angle? From here around to here. We need to know that our angles add up to 360, so 360 subtract this gives us our answer. So this angle here underneath B is going to be 219 degrees, because 360 subtract the 140 gives me 219. And therefore we can now figure out what angle ILK is. ILK is going to be half, because it ends at I and K, and this angle here that goes around here also ends at I and K. They have the same arc along the bottom. This one in red has an arc along the bottom. The one in green has an arc around the bottom, and the one in green is 219, so the one here has to be half of that. So 1/2 of 219 is about 109-ish, and I'll get the computer to calculate that to show what it is exactly. And there it is at 109.79. So we can, given just this angle down here, figure out what this angle here is by using our central angle. Now we might also notice that if I take these two angles and I tell it to add them together, this angle, and we're going to add it to this angle, what number do we get up? We get up to the answer 180 degrees. And we're going to find that opposite angles inside a quadrilateral, if all the points are inscribed on the corner, opposite angles add up to 180 degrees. So we've talked about inscribed angles, being half of the central angle. Inscribed angles that go to the same points are equal to one another. We've talked about inscribed angles that are in the special situation with a diameter being 90 degrees, and we've talked about how we can find out angles opposite to one another in a quadrilateral, inscribed adding up to 180. So we've covered a lot. We're going to move on to talking about some of the characteristics of a chord of a circle. Recall in the last segment that a line segment going from one edge to the other is called a chord in my circle, and there's certain properties of a chord that we're going to notice. So if I take and select my center of my circle and my chord and ask us to construct a perpendicular line, it's going to go through at this point right here. So if I measure it, if I put a dot there, now I can ask the computer to calculate the distance from here to here. And it measures the distance, and if I ask it to measure the distance from here to here, measure the distance please, what do we notice? We notice that if I take a perpendicular line to my chord, it's going to cut it exactly in half. And it doesn't matter if my chord's over here, or if my chord's over there. It doesn't really matter how I do it. If I make a really big chord, a perpendicular bisector cuts it in half, and if I even make it something that looks like a diameter, it's going to cut it in half, and that makes sense because my diameter is made up of two radii that are exactly the same. So changing my chord, I can show that if I perpendicularly draw a line, it's going to cut it into two equal pieces. Now related to that, I can say, well, if I have a chord and I want to find where the halfway point is, so I'm going to tell it to put the midpoint. If I connect my midpoint to my center with a line, and I ask it to measure the angle, I'm going to find out something that always happens. And that angle is always going to be 90 degrees. And that's working with the last one that we talked about. Last time I put a 90-degree angle in and notice that it produces something that's halfway, cuts it into two equal parts. This time I started with the halfway point and it creates an angle of 90 degrees. So I created one before and it cut it in half. This time I had something cut it in half and it created the angle. This perpendicular bisector idea is the concept we're trying to get across. One of the applications for this is trying to find the center of my circle. So if I had a circle and I didn't know where the center was, let's do that. There it is, and I want to find out where the center is. I can use my chords to help me figure that out. So I've got a circle, I don't know where the center is. I draw a chord pretty much anywhere, it doesn't really matter where it is, and I draw another chord, and I mark exactly where it is halfway. Now I take a protractor or a square edge that I might have in my shop, and I want to make a 90-degree angle from this center piece. So I click on the line, my center piece, I want to construct a perpendicular because I know we're going to have perpendiculars. I do the same thing with this one. I construct in the center, please make a perpendicular line. And where the two perpendicular lines meet, we know it has to go through the center of the circle. And if we do that, we can find the center of our circle. And it doesn't matter which chord I use, of whatever shape, whatever length, it has to be going through the halfway point, the midpoint, and it's always going to go through the center of the circle. So if I'm building a project and I want to find the center of my circle someplace, I can use this chord property and the perpendicular bisector, two of them, to find the center of my circle. So in this segment we talked about inscribed angles and central angles and chords and the properties that are involved with all of those. I'll do tangents in the next segment so this one doesn't get too long.